The purpose of this lab was to investigate the physics behind the world's largest rope swing, and that video can be found here. We're going to relate the jumper's motion to the motion of a pendulum, and the results are that we can predict the motion of the jumper using the energy principle and the momentum principle. So here are the initial conditions given in an explanation video of the rope swing. The length of the rope is 45.72 meters. The drop is 39.624 meters. At the bottom, the rope is 3.048 meters from the ground, and the mass of the jumper is approximately 70 kilograms. And the angle at the bottom of the swing is 90 degrees. So here we apply the energy principle in order to find the final velocity. The work is zero, so that means that the change in energy of the system is zero. And we only have final kinetic energy and initial potential energy. So when we do this calculation here, we find that the final velocity is 27.9 meters per second, which is approximately 66 miles per hour. Here we are calculating the tension at the bottom, where the tension is going to be the greatest, and also the velocity will be the greatest at the bottom. At the bottom, since there is no parallel force, we can say that F net equals F perpendicular. And then we know that there are two forces, tension force and gravity force, T for tension and mg for gravity. And then we can say that F net equals mv squared over r. And the radius is just the length of the rope, which is 45.72 meters. Here we find the final velocity at 30 degrees from the center of the rope swing. And we know that the initial kinetic energy is zero, and then we can find that the final velocity at 30 degrees is 24.5 meters per second. And then we can calculate the tension at 30 degrees. So we know that they missed the ground by about 10 feet, which is about 3 meters. So we can say that the height at 30 degrees is going to be the height at which we started plus 3 meters. Thus we can say H equals L minus L cosine theta, and we found the height to be 6.13 meters. To find the height at 30 degrees, we can just add 3.05 meters to H to get 9.17 meters above the ground. And then we can apply the tension force yet again, and the force tension at the bottom is 1,512 newtons. So here we are finding the stretch of the rope at the bottom, and we use the ideal spring force because we wanted to treat the rope like a spring. We used the tension force that we calculated, and we found the spring constant online, which is 29,000, and then we found our stretch. So we do the same thing and calculate the stretch at a 30-degree angle. So we just use the force tension at a 30-degree angle that we previously calculated and use the spring constant of 29,000 again to get this stretch. So now we're going to look at the code. I based this code off of the code from the spring lab since the rope swing behaves similarly to the spring. The rope just has a larger KS. So here you can see that I put in the gravity, mass, L naught, and a very large KS. Then here is L, which can tell us where the jumper is in relation to the rope. And then here is the force of the spring. And then here we are updating the position using the momentum principle. So if we run this code, you can see that the model matches very well with the motion of the pendulum and the motion of the jumper in the world's largest rope swing video. So the two arrows represent the force tension and the momentum. And also the code can output the calculations to exactly what we calculated them to be in the previous slides. So in conclusion, the model is successful at predicting the jumper's motion using fundamental principles such as the momentum principle and the energy principle.